Hello everyone. Have you ever saw a core material data sheet? Like we might have seen a data sheet of MOSFET, capacitor, resistor, BJT, and other devices. But like I don't think like many of us see the material data sheet of inductor and transformer. So in the data sheets of MOSFETs, resistors, capacitors, we get the direct value of those uh, compound those components, but this is a material data sheet which is from which you can design your inductor and transformer. So this is a manganese ferrite material, a manganese zinc ferrite material data sheet, and so this is used to design high frequency inductor and transformer, which are used to in applications like SMPS and Flyback, and application areas of telecommunications, power conversion, interference suppression, and they come in many forms like toroids, ecores, eucores, icores, and podcores, and they have good magnetic properties like low Curie temperature and high electrical resistivity, and these are used for very high frequency up to megahertz. This is just a basic overview of this material data sheet, and let's go deep into it. So these are just a base example dimensions for this core, and these are the magnetic characteristics of this core. So the effective area of the core is 1550 millimeter square, and this is mean magnetic path length, and the weight is 2.5 kg, and the grade is ferrite N87, which is very famous. So like if you are into electrical lab, you can use this core to check it. Okay, so this is the setup for it. You can connect a voltage sensor, current sensor, with oscilloscope, and use a function generator and RF amplifier, and that's the setup. You can use it to test the core. So there are very important two formulas here. One is this strength formula, which where you can use the primary number of turns and current and mean magnetic path length and calculate the field strength. And the second one is to calculate the flux density, where you are using secondary number of turns, effective area, and the voltage. So these are very two important formulas. Secondly, here if you're seeing these waveforms, so generally in SMPS design, we do all the calculations by considering the sine wave, but in the practical scenario, we most of the time don't get the sine wave. We get the trapezoidal waveforms. So that is like when we study the power electronics and see all the waveforms and all, there we get the idea like, okay, in the practical scenario we get trapezoidal waveforms. So this is how the effect of different types of waveforms on flux density. So this is here sine wave, and this is here sawtooth wave, and this is here trapezoidal wave, and the effect um, density for it. And this is the and has BH curves for the low frequency BH loops representing here. And like if you see, these are the different parameters for this curve, where which you can use from here. And these are the different graphs for uh, BH curve for different permeability. This is relative permeability, and this is incremental relative permeability. And this is the third important formula, which is Steinmetz equation, which is used to calculate the core power loss, where you use the frequency and the field density to calculate, flux density to calculate the power loss. And this is the BH curve as a function of frequency. And here you can see for different types of waveforms with different duty, different parameters values are given. And these are the waveforms for the losses at different frequencies and the flux density accordingly. And this is the core permeability waveforms, the practical ones, which they have shown here for flux density for different frequencies and the relative permeability. So one of the graphs we see, the density is going from 0 to 0.09, and the relative permeability is going from 2000 to 3800. And if we see, there are like five uh, lines for 10 kilohertz frequency and till 200 kilohertz frequency. And if we see the 200 kilohertz frequency, it is shown here at low relative permeability we have low flux density, and at high relative permeability or high a little bit high flux density we are getting high relative permeability. And if we go for like here, it is flux density and the relative permeability with respect to duty cycle, d equals to 0.5 10 kilohertz, and this is a fixed duty of 0.5 with different frequencies, 10 kilohertz, 20 kilohertz, and 50 kilohertz. So from here we can see the highest one, top one. So for sawtooth, I think SAW is for saw tooth waveforms, and this is the duty cycle 0.5 and at higher frequency. So at lower flux density we are having low relative permeability for this 50 kilohertz frequency, and this is at around 0.7 flux density, or at a higher relative permeability we are getting 0.7 flux density for 50 kilohertz. And this is the third waveform for duty cycle of 0.3, and same for like different frequencies, the lines are given. And this is they are reducing the duty cycle. So from there we can also see at a higher duty cycle, which is 0.5, and higher frequency 50 kilohertz, we are getting we are getting permeability of I think this is 3300. And similarly we see here the flux density is also increased, it is going till 0.08 and it is 3600. Similarly we see here for duty cycle 0.1 and 50 kilohertz frequency, we are getting a flux density of 0.07 and the relative permeability of 4600. And if we see here at 0.3 duty cycle for trapezoidal waveform, which is the practical waveform we get in SMPS, we at 30% duty cycle and 50 kilohertz frequency, we are getting around 0.02, almost 0.06 with 3200 300. So if we see this one 0.03 and this one, so the values are almost similar but the lines are different. But if you see, the values are almost similar for this. So this is all for trapezoidal waveform. So if we see for trapezoidal, for lower duty cycle, you get low flux density and a higher relative permeability. And for a little bit higher duty cycle, for higher frequency, you get low flux density and low relative permeability. So I hope you got some learning from this video. And if you like if you have any queries, or if you would like to discuss something, you can mention in the comment section. Thank you.